All right, thank you for joining me today here at Subsurface Live Summer 2021. I'm excited to be here with so many of you from so many different countries. And today I'll be talking about the future of data infrastructure and specifically 3 key trends that are shaping that future. The first trend I want to talk about is the shift towards open data architectures. We all remember from a decade ago that the way data architecture was done was a very closed and proprietary one. You basically had databases like Teradata, Oracle, and many others, where you had the storage, the data, and the compute all co-located in a single system. So if you wanted to use any of these systems, you would have to basically ingest the data into that database, and then you could use whatever that engine that came with that database was. Teradata came as, say, an appliance, and with Oracle, maybe you'd mount some external storage, but the data was tied to that one specific engine. What started happening when public cloud became prevalent was the rise of this new architecture in which storage and compute are separated. And what that means is that the database itself can leverage behind the scenes things like S3 or Azure storage to create kind of more flexibility in the architecture, but still the data is stored in that system in a proprietary format. So if you're using something like Snowflake or Redshift, you're ingesting the data into that database, and you can only use the capabilities that come with that one database to actually analyze or manipulate that data. And so there's a lot of limitations with this, and that includes, for example, the fact that there's significant vendor lock-in here. It becomes very difficult to get off of a database or a data warehouse in this kind of architecture. That also means that the prices become very high, and that typically goes kind of hand in hand with the vendor lock-in. What's happening now is the shift towards open data architectures, and this is something that we're very excited about. So in this architecture, the data itself is its own tier. It's stored in open source formats, open source file formats like Parquet files, JSON files, open source table formats like Apache Iceberg and Delta Lake. And on top of that, then you can have many different engines that can access and manipulate that data. So at Dremio, we've always been focused on the SQL use case, right? Things like BI workloads, being able to run ad hoc or dashboards on that data. But there are many other engines that people use on that data. Things like Spark engines from companies like Databricks and AWS and Microsoft. And one of the nice things here is that you can choose the best of breed engine for a given workload. Not only that, but in the future, as new engines get created, you can choose those engines as well. It becomes very easy to spin up a new engine, point it at your data, at your open source Parquet files or your open source Iceberg tables, and start querying and modifying that data. So when you have this open architecture, one of the other benefits is that it leads to a very rich ecosystem. And actually, if you look at the speakers at this event, which are the logos that you see here on this slide, you'll see that they represent many of the world's largest tech companies, as well as various startups and open source innovators. And all of this innovation is basically being made available to you when you use an open architecture. Well, that might lead to the question, well, are open architectures inherently harder to manage or use, right? Because if you have different moving parts, well, does that make it harder? And I think the easiest way to answer that is to look at an analogy, something like this that we've seen before. And actually, if you look at what happened with application architectures and application development, we've seen a very similar transition. We've gone from monolithic applications to microservices, right, where you have decoupled services that are independently scaling. And I myself used to be a developer, and I built a lot of web applications, initially using things like ASP.NET on top of SQL Server, and then using things like Django and PHP on top of MySQL. So very monolithic architectures. And today everyone's creating microservices. And one of the things that's enabled that to happen is the tooling, and these technologies have really made it easier, right? Things like containers and Kubernetes, right, that have made it easier to build applications in this new architecture. Well, the same thing now is happening in this transition from cloud data warehouses, that closed architecture, proprietary systems, to cloud data lakes and lakehouses, right? This open architecture. And the two main things that have to happen with open architectures in order for them to become easier over time are, number one, we have to make the infrastructure easier, and number two, we need to make data engineering and management easier. And if we can do those two things, it becomes very easy to have the benefits of the open architecture with, really that ease of use that we all want to have. So the second trend I want to talk about is how we make infrastructure easier. And I think a lot of that comes down to this transition from engines to services. And I know I've talked a lot about engines over the last 10 minutes, but really what we're starting to see is that more and more, rather than running software inside of in the cloud or inside of systems like Kubernetes, that ability to leverage SaaS services makes it a lot easier, right? You don't have to deal with software, you don't have to install anything or worry about upgrades or configuration or tuning. You can really work with these services the way you work with things like Gmail, right? You create an account, you log in, you start working with it, right? And these different services can all talk to that same open data tier, right? Those same open file formats and open table formats. Not only that, but in the future, what you'll see is the ability for these services to communicate with each other directly, because we're creating standards today that will enable that kind of very, very fast, very high performance integration between services. Specifically Aeroflight, which is part of the Aero project that we co-created years ago and is now downloaded 20 million times a month. With Aeroflight, different Aero-enabled services will be able to talk to each other much faster than before. Now, with respect to services, today I'm very excited to announce the availability of Dremio Cloud. Dremio Cloud is Dremio's SaaS offering, and it provides a SQL Lakehouse platform. And if you look in the chat right now, what you'll see is our virtual t-shirt cannon. If you click on that link, over the next few minutes here, you'll actually be able to get one of these Dremio Cloud t-shirts. So what is Dremio Cloud? Well, it basically combines the things that people love about Dremio today, right? The reason that hundreds of companies use Dremio to power their cloud data lakes today, including many of the world's largest companies, such as query acceleration, right? The ability to have sub-second response times and very fast performance on data lake storage without having to move the data into a data warehouse. The self-service semantic layer, which creates a unified and consistent view of the data for everyone in the company, all users, all tools, also allows you to apply kind of security and governance on that data. And then our best-in-class integration with a variety of BI tools, such as Power BI and Tableau, right, with native integration and single sign-on. So we can now combine that with the ease of use that comes from a true SaaS experience. Not having to deal with software, so there's nothing to install, there's no upgrades, there's no versions, there's no boxes to SSH into, configuration files to deal with, you don't have to collect log files to troubleshoot things, just a much easier experience. And then also infinite scalability, so the ability to run as many queries as you want and not have to worry about whether I have one query a day or 1,000 queries a second. So this is very much like if you think about services like S3, which we all love because we can put as much data as we want into that system and not have to worry about, is there enough capacity? Is it going to get slow, right? Same thing with Azure storage. So we wanted to provide that kind of limitless experience for querying data. And then finally, workload isolation, because nobody likes it when the interns submit queries that are really, really complex and they impact the CEO's dashboard, right? And in most companies, we have a variety of workloads and we don't want any interference among those workloads. Of course, at Dremio, we've been dealing with many of the world's largest enterprises, many of the Global 2000, and so it goes without saying that world-class security is something that we built into the platform from day one. And then on top of that, one of the unique things we've done with Dremio Cloud is we've created a global control plane so that you can have a single pane of glass regardless of which clouds or which regions you're using. You can see all your data, you can define permissions and see all the privileges that you've granted, whether on data or on other objects, in a single list, in a single place. You can see who has access to what. You can see all the integrations that you have with your IDPs, your identity providers, different applications. All of that shows up in one place. And that's the value of having a global control plane. Now, how this is architected, if you look at this slide, it basically shows you the architecture of Dremio Cloud. So the engines which are executing the queries, we spin them up in your VPC so that they can run next to your data. Because a really important part of this architecture is that the data stays in your S3 buckets, in your control, and you're not having to take that data and give it to somebody else. And so we run the compute close to the data. And you can create different engines for different workloads. This is what provides workload isolation. So maybe a medium-sized engine for the executive dashboards and an extra large engine for data exploration. Each of these engines is auto-replicating. So whether you have 0 queries at night and there are 0 replicas, or it's Monday morning and everybody's hitting the same dashboard, and then you have 10 replicas of that same engine, that is all handled automatically. Now on the left, what you can see is the BI tools, right, and other data science applications. And we've created very nice integrations in partnership with these companies to Dremio's control plane. So if you take a tool like Tableau or Power BI, they come with native Dremio connectors with full single sign-on based on OAuth 2.0, and they can connect to that global control plane and send the SQL queries directly there. And then the control plane has an infinite amount of query planning capacity. So again, regardless of whether you're running one query or thousands of queries at the same time, you don't have to worry about that. We take care of that in our control plane. The control plane then uses query routing rules that you can create in the system to decide which engine is going to handle which query. So the queries are assigned to engines based on rules such as who the user is, what groups they belong to, what type of query they're running. And then, of course, a user can also explicitly select an engine if they have the permission to do that. So to make this more real, I want to invite Jason Hughes, who's a technical director at Dremio, to show you a demo of Dremio Cloud.
Thanks, Tomer. So, in this demo of Dremio Cloud, we'll frame it really in 2 personas. The first being a data analyst. So we'll actually go through performing BI analysis directly on our cloud data lake using Tableau. The second is really from a data scientist perspective. So we'll actually simulate a group of data scientists across an organization, all running their ad hoc exploratory kind of analytics. And really we'll show, instead of running one and then the other, we'll actually run them both at the same time to show how Dremio Cloud really seamlessly handles that, because in the real world, that's what you have, is these heterogeneous workloads running at the same time. So here we see that Dremio Cloud has a multi-engine architecture. So we can see here the set of engines that are actually defined in our environment. So one of note is the data analyst engine. We can see here that it's a size medium, and here we see details about the replicas for this engine. So a replica is basically the unit of scaling within an engine. So we can see here that the data analyst engine is configured to have a minimum number of replicas of 1. So there's always something running in this engine to be ready to interactively respond to any data analyst queries. It also has a maximum number of replicas of 10. So this basically says Dremio Cloud scale depending on workload, just automatically scale from 1 replica to 10, but don't scale past 10, because we want to control our costs in this way. We don't want to scale to 20 or 30 or 40, which you could certainly configure Dremio Cloud to do as well, but allows you to provide that control. The other engine that we see here is the data science engine. It's also of size medium, and this one, unlike the data analyst engine, actually has minimum number of replicas set to 0. So this is basically saying that, hey, when if there aren't any data science queries running, just shut the whole engine down. And basically what you can see here is that there's no replicas running because there are no queries or no workload running on this engine. So this engine is costing us nothing. So let's actually go ahead and kick off the data science workload. So we can go here and we can actually run this demo script, which when I run this will actually kick off 100 concurrent queries against Dremio Cloud. So it'll actually continuously run 100 concurrent queries in the background. So here we can refresh the jobs page and we can see the job start to come in, right? We can see the job here, and it's actually kicking off the engine start. So it's actually going ahead and kicking off the initial replica. Now we have 1 replica that's running. We have 4 nodes within this replica. So these will actually go ahead and start up, and then the rest of the replicas will in fact start up to handle the concurrency that we issued. So let's change hats and actually go into the data analyst scenario. So as we do that, keep in mind that the entire time we go through the rest of this, there will actually be 100 concurrent queries continuously bombarding Dremio Cloud. So from a data analyst perspective, we actually want to go ahead and perform trend analysis on taxi rides in New York City. So we'll go ahead and select the business zone of our semantic layer. We can see here the transportation folder. And we see here a data set called NYC taxi trips. We want to go ahead and select that, and Dremio will bring us a preview of the data. So we can see here that we have the when they were picked up, when they were dropped off, passenger count, etc. We can see that these are in fact individual taxi rides. So each record in here is an individual taxi ride. And in fact, in this data set, it's actually 1 billion records stored in our cloud data lake. So let's go ahead and perform our trend analysis. So with the data set pulled up here in Dremio, I'm going to go ahead and click this quick launch button for Tableau. And it will download a small pointer file. So I'm not downloading any data. That would certainly take a while. It may not even fit. And it will launch Tableau. Basically pointed this data set, pointed this instance, and in it, it also says, Tableau, I'm actually configured for single sign-on. So Tableau will automatically launch me to a web page where I go ahead and log in. So I'm going to go ahead and log into Dremio Cloud, and here we can see that this is the organization. I'm going to log in with Google because that's basically our enterprise identity provider is G Suite. I go ahead and select my Dremio account. It'll go ahead and authenticates me, and then it sends the credentials to Tableau, and it basically says, hey, you're now safe to close this window. Great. Go back over to Tableau, and I have my data set pulled up, right? So I didn't have to type in or manage any credentials here. I just used my normal identity provider that I use every day. So let's perform trend analysis. Let's look at number of rides, over time to start. And number of rides is really, again, because one record is a ride in the table, we actually want to do the number of records in this data set. So we take that and we drag that into the shelf, and we see that Dremio comes right back and says, okay, yep, you have actually over 1 billion records in this data set, which is, again, stored in our data lake storage. So let's look at, again, number of rides over time. We go ahead and pull in the pickup date time, defaults to year. That's great. We can, change it. We can look at quarter instead. We can go ahead and pull in additional measures like the tip amount. We can change it from, it's sum by default. We can change it to average. Note that every single one of these clicks that I make in Tableau, which comes back interactively, right? It comes back right away, is actually a live query back to Dremio. So if I go ahead and pull up Dremio and go back to the jobs page, here we can see the data science query is starting to complete, right? We have some completed, some still running. If we actually go ahead and refresh this, here we can see the queries from Tableau, right? So we can see the SQL that was ran, and we can see that all of these were actually replied to by Dremio in under a second. So actually sub-second response times, which was providing that interactivity for us in Tableau as a BI user. And here we can see that it's actually getting routed to the data analyst engine, right, as we wanted it to. Meanwhile, while we were able to provide that interactivity for the data analyst, the entire time there was still all of these queries running against Dremio. Right, we see some still queued. We see quite a few running. So again, now we start to see the remaining ones start to run, because if we actually go back to the data science engine, we now see that we have 9 active replicas. So these are all the nodes that are currently running within the environment. Right, so this was able to automatically scale out. And now if we actually go ahead and cancel this script, so this will basically terminate the connections with Dremio. Right, so it will basically cut that off. Dremio will actually automatically recognize, of course, that the queries are starting to cancel, which, when it hits the timeout, which basically it does there. And then what it'll do is after 1 minute, so we've canceled all queries on this engine, right, using our script. And after 1 minute, it will actually automatically deprovision all of these, basically the replicas as well, right? Because we basically configured it that way. We said, hey, when there's nothing running, go ahead and shut it down quickly. So while we wait for that to shut down, just to quickly recap, really what we saw. Certainly on the Tableau side, really on the data analyst, we were able to provide certainly a streamlined user workflow, right? We were just able to open that pointer file. We're able to open up Tableau, launches Dremio. We're logging in using our identity provider, right? We just did a couple clicks that we do every day. We're able to get our authentication set up, which then also provides for the IT side, the authorization, audit logging, governance, things of that nature. We also saw, in the data analyst, really the performance, right? We still saw that sub-second response time, regardless of there being, all of these other workloads happening in the background, and IT didn't have to manage any of that as well. Now that we see, certainly around the scalability, that the data science engine automatically scaled out, right? It automatically scaled out to handle the workload that it saw. And now that the workload is not there anymore, right? Or there's at least less workload, we see that the nodes and really the replicas are starting to deprovision. We see now that we're back to 1 active replica. And so basically we're able to manage that really cost and performance trade-off, right? We're able to manage that in this way automatically with Dremio Cloud. We also saw really on the isolation, right? We ran both of these workloads at the same exact time the entire time that we were going through this, right? And we didn't see any effects. IT didn't have to manage anything. Dremio was automatically scaling out both on the query planning side, on the control plane, the globally distributed control plane, as well as the really on the execution side with the engines, right? It was automatically scaling out the execution resources that we needed. So thanks. Back to you, Tomer.
All right, thank you, Jason. That was great. It was really exciting to see all those data science queries. 100 of concurrent queries, and still having that sub-second response time for the Tableau dashboard. That's something that I know many people will be excited about. So thank you for that demo. If you'd like to try this out, simply go to dremio.com/cloud and you'll be able to sign up there. So the next thing I want to talk about, and the last of the 3 trends that I wanted to cover today, was how do we make data engineering and data management easier? So about a year ago, I was talking to the head of data engineering at one of the big tech companies, one of our customers at Dremio. And the way he described the dream of every data engineer was that in an ideal world, the data engineer who's trying to maybe change some data or make a modification would be able to do that in isolation, right? They'd be able to do it kind of in a sandbox to make the changes and then verify that they've made the right changes. Once they're done with that, they would take that and publish that in one atomic operation, right? In one transaction back into the data lake. And so there was never a state where things are inconsistent. And the data engineer who's modifying the data is never working on the live environment, never in this risky situation where they might mess up and all of the analysts and all of the data scientists that are consuming the data are in a difficult situation. And then on top of that, one of the really important things that every data team wants is an undo button, right? So that you can't mess up. You can always go back in time. You can always revert the last few changes if you have to. And that means, the chances are you're never going to be stuck working all night to fix something or working the weekend because you've left something in a bad state. This is now becoming possible. This dream scenario, because of a number of new technologies, is actually about to become reality. And one of those technologies is the rise of open source table formats, things like Apache Iceberg or Delta Lake. And so Iceberg, for example, is a project that we're excited about that was created by Netflix and has many contributors from many of the largest tech companies now who use Iceberg for their data lakes and lakehouses. And it provides a number of key benefits. But fundamentally, it's providing a transactional table within the lake. So for example, the ability to perform mutations at the record level with DML operations. You can insert a record or update a set of records or delete records that match some condition. You can create partitioning schemes when you're creating a table or modify the partitioning schemes, and users don't have to worry about that or know about it. The queries actually don't specify what the partitioning key is. And then if you ever want to change that partitioning key or one of the keys, or if you want to change the schema of a table, it becomes very easy to do that. It's basically one simple alter table statement that you have to run. And it finishes instantaneously. It doesn't take any time. And then also the ability to query a specific snapshot. So as I mentioned, these formats are transactional. They kind of move forward in time. So you have the ability to query a previous snapshot at any time. Iceberg and Delta Lake operate at the single table level. And what we've done at Dremio is we've created another open source project called Project Nessie, which provides a new and more modern metastore for the Lakehouse. And we've actually borrowed some of the concepts that will probably be familiar to most of you from the world of Git. And these 2 concepts that we've borrowed are data branching and data version control. So for data branching, which basically provides transactions as well, you can create a branch, as you can see in this example, where we're creating an ETL branch, which we then use. And we do these things from SQL. We can then insert into that table, update that table, and then merge that branch back into the main branch, the main view of the data lake. So all the analysts and the data scientists can actually see those changes as one atomic operation. In addition, in terms of data version control, you have tags and commits. And those are kind of consistent, transactional at the entire data lake level. So you might create a tag for the end of month financial data for August, as you can see here. And then go back and say, you know what, I want to use the July end of month data to see how things compare. And so you can select star from a number of tables as they were when the tag July end of month was created. And you can even do that at an individual table level within a SQL statement using the @ character. So it turns out that this approach is actually much more aligned with kind of how data engineers work, with the real world. And if you compare this to database transactions, which were really designed for OLTP applications, right? They were designed for a world in which you have one session, one user, everything's being done from SQL. Right? This would be great if what we were talking about was moving money from one account to another account. Right? If you're an app developer building an app, these types of transactions are exactly what you want. Right? You run a begin transaction command, you do a number of inserts and updates and maybe some deletes, and then you call the commit statement, and that's a transaction. But that's not how data engineers work, and that's not how the real world operates, right? How companies work. In the real world, you typically have multiple sessions, multiple users, potentially multiple different engines and services that are operating on the same data. And that's much more aligned to how data engineering teams work, right? And so in this example here, what you can see is that we've created a branch called ETL, and we then ingest data from Kafka. Maybe we run some bulk export from our RDBMS. We then run various Spark and Dremio transformations, maybe some additional SQL statements or Spark jobs. And then when we're done with all of that, and maybe that took an entire afternoon or entire week to actually get the data ready to the state that we want it to be in, we can then go back to the main branch and merge the ETL branch into it. So to make this more real, I want to hand this over to Tom Fry, who's the director of product at Dremio, and he's going to show you a demo of what this actually looks like.
Great. Thank you very much, Tomer. So to demonstrate the power of Nessie and its ability to work on multiple different versions of the data lake at the same time, today we're going to walk through a quick scenario with two independent personas. The first is a sales manager here, and this sales manager is looking at the data lake to identify the top customers in the current month across multiple different tables within the data lake. We can see here that the current month is 6 for June, and that they have a certain set of top customers in the current month. And they're always running this against live production data. The second persona is a data engineer. And this data engineer needs to go through a typical ETL process to update the data lake. But they want to do so in a protected, isolated version of the data lake so that they can make sure that everything's okay before publishing data to users. The first thing we're going to do is look at what versions exist within Nessie. And we can see here that we have one main version, which is for production data. And it's actually very easy using Git-like semantics, which software developers always do, to create essentially a new branch for ETL data. And now we can see that we have two different versions of the data lake, our production version and an ETL version. But they're both the same with the same commit timestamps, the same commit hashes, because we haven't changed anything. The next thing that we can do is we can look at what context we're working in our current SQL session. And we're currently operating on the production version of the data lake. However, it's very easy and trivial in Nessie to jump between different versions of the data lake. And can we see now that we've switched our session over to the ETL version so that all of our changes are made within an isolated version with Nessie. The next thing that we can do is use Apache Iceberg to insert new data in a transactionally consistent manner into multiple different tables. And now when we look at what versions exist in the data lake, we can see that our ETL version of the data lake has moved forward and we have new commit hashes because we've modified it. However, the production version of the data lake is still the same. And in fact, even though we've inserted July data, our sales manager who's working against the data lake is still seeing June data with the month 6. Now our data engineer wants to verify those changes. And so this is a quick query to make sure that all orders have an associated customer. And we can actually identify here that there's some orders that are missing a customer reference. We actually have a foreign key relationship problem here. This is a failure scenario. This means our data lake is currently in an inconsistent state. This is a type of scenario that happens quite often, usually at 3 in the morning. It's when data teams have to run around and figure out what's wrong and how do I fix it. However, in this scenario, even though our updates are broken, we can see that our sales manager is not exposed to them. Our sales manager is still working on published and verified June data. The next thing our data engineer can do is fix the ETL branch. There's actually a couple ways they could do this. The first is they could drop the branch and start the process over. Just like in Git with software developers, creating and dropping branches is essentially a free operation, even if here it's against a petabyte-sized data lake. Another option we can do is fix the version that we're working on. And so what we'll do here is we'll do that. We will update our customer table and fix the data lake, and we can do so and rerun our verification checks and find that yes, all orders have an associated customer. The last thing that our data engineer wants to do is publish this data, and they want to do so in a transactionally consistent manner, even though we have multiple tables in the data lake. So the first thing that we're going to do is switch back over to production context, and we now can run a merge statement, which updates the entire data lake with the changes from our ETL branch. And what we can also look at is now we can see our versions of the data lake are the same because we've taken our ETL changes and published them to the production version of the data lake. One of the powerful things here is even though we have multiple different tables in the data lake, all of these tables were updated in a transactionally consistent manner, just like you would see in a regular database. Now, if our sales manager runs the exact same operation against the data lake, he now sees July data and the new set of top customers for July because we've published the July data. But he's seen this in a consistent manner with verified data. The last thing that we're going to do is reproduce past results. And so what we can do with Nessie is create tags for historical versions. So first we'll create a July tag for the latest data, and we can now see that we have two different historical reference points. One is for the June data and one is for the July data. And we can also see that we're currently working in the production version of the data lake, which has July data in it, but it's also very easy to switch between different versions. Here we're going to quickly switch over to the June reference point. Now we can see that we're currently operating on June data. It's read only because historical data is immutable and cannot be updated. But actually with Nessie, we could create a fork of it and do experimentation purposes on historical data in another private version. But what we can see here is since we switched over to the June reference point, across all tables, we're now looking at June data. It's also very easy to switch back and forth. We can switch over to the July reference point, and even though we're referencing multiple tables, we can now see that we're seeing July data. And so it's very easy to switch between entire versions of the entire data lake environment. This enables people to reproduce past results, for example, with machine learning models, and show what did they reproduce to answer what-if questions 3 or 4 months ago. And it's possible to reproduce the exact same results that you had in the past. So we're very excited about this. We know a lot of our customers that we talk to are very excited about this, and it's really going to help data engineering teams with a lot of the operational challenges that they face with today. So thank you very much, and back to you, Tomer.
All right, thank you, Tom. That was really exciting. So hopefully all of you are as excited as I am about these types of capabilities that are coming to our cloud data lakehouses. So if you're interested in learning more about what you just saw and some of the technologies that are involved, such as Nessie, Iceberg, and Delta Lake, we have a number of talks lined up for the next couple of days. So please go ahead and attend these. And actually in half an hour, we have Ryan Murray talking about distributed transactions on the data lake with Project Nessie. So he'll share a lot more technical information about what we just saw. So thank you again, everybody, for joining me today. We have thousands of people joining from all over the world. I'm excited to have you here at Subsurface, and I look forward to chatting with you some more over the next few days.